In this video, I'm going to go over this so-called simple 8-bit assembler simulator um, and go through the Hello World program. And I have a sort of an elaborate slideshow on it. I'm going to break it down into sort of three parts, three videos. And the first part will talk about sort of the setup, like what the architecture is, and then in part two we'll sort of start the program, and we're in order to sort of display hello world, we're going to have to loop through the each character of the string, so we'll have the H and then the E and the L. So then I will sort of go in the second video, I'll go through the sort of an iteration of the loop and get the H and maybe set up to get the E. And then I will, in the end, sort of work on the last iteration of the loop and then end the program. So here we go. So let's just sort of start it here. Set up, we have this a bunch of registers. So I'm going to move, let me just step through it a bit here, and then I'll move over to my slideshow. So we step, and that sort of program is loaded here in memory, and then we can start sort of stepping through it, and eventually we get to the point where we see here's the H. So this is it's part of memory, but also part of the output in what's called memory mapped output. And then I start to see many, many steps to get the E, many, many steps to get the L. And that's what I want to sort of talk about here. All right, so let's begin this slideshow. Here we go. All right, so here is this assembler simulator, and it has A, B, C, D are registers. IP is the instruction pointer. SP is the stack pointer. And then we have what I'm going to call some flags. And in this program, we're going to use the Z. Okay, so again, just repeating. This A, B, C, D are registers. Registers are places where you can sort of temporarily hold a little bit of data, because this is sort of an 8-bit architecture. So those registers are holding 8 bits, which is going to be seen here as 2 hexadecimal digits. The IP here stands for instruction pointer, and it tells us the line of code that we are working on, that we are executing. So I'm used to sort of even more detailed program or architecture at some point. And sometimes I talk about a program counter and instruction register. But this thing here called the instruction pointer is sort of those two things combined. So it's telling us where we are in the program. And sometimes it will be incremented, not necessarily by 1, but by something. And that increment will move us to the next line of code. But we can also put things in there, so we can jump, and we will need to jump if we have loops and subroutines. And in this little example, we're going to have the sort of printing out of the string in a subroutine, and that subroutine is going to involve a loop to get us through all of the characters of Hello World. We have part of memory that is designated as the stack pointer. So in regular RAM and regular memory, we can access any location, any value at any location. But when we designate part of the RAM, part of the memory as a stack, then we limit the way that part of memory can be accessed in a protocol known as LIFO, last in, first out. And so when we want those rules followed, then we use that part of memory known as the stack. So here in this picture, we see that the stack pointer corresponds to memory location E7, and then the stack is going to work backwards from that E7. So in that direction, I'm showing with the red arrow there. Um, on the other side, starting at E8, the those memory locations are sort of shown in that light gray, and that these are the memory mapped output. So those uh, locations are also connected to some kind of a display, so that if there's something in there, right now there are zeros in there, so maybe we should be displaying a zero up at the top, but we will later, when we put the sort of ASCII character corresponding to the capital H of Hello World, we will see if once we get that H in this memory location, then it will appear in the output. So that's just a part of memory. There's a special, we'll talk about RAM in general next, but there's a special part of a memory called the stack, indicated by that sort of amber color, uh, and the stack pointer SP. And then we have the memory mapped output, which is shown in the light gray. And so as we put things in there, we will also, a user would also see them in the output. And then we have these flags, these results of comparisons or indicators if something went wrong, like an overflow or something like that. So we're going to be asking some question and putting the result of that question, some kind of comparison, and putting that result into Z, and then asking questions about Z. All right. And then, so those are all the little special things. And then there's this big bulk thing, the random access memory. So random access means that it's an addressable memory. You supply an address, and then you can get the value at that address. In this case, our addresses, our locations are 8 bits. So we are going to, each address is going to correspond to uh, 8 bits, and we're going to break those 8 bits up into 2 hexadecimal characters. And so then we're going to have 256. So the 8 bits can correspond to 256, or if we're thinking of them as 2 hexadecimals and there are 16 hexadecimal characters, that's also 256. And so there are these 256 locations, and we're going to think of them as a sort of a two-dimensional array as we're showing here. So there will be sort of a row and a column. So when we express the address as 2 hexadecimal digits, one of them is sort of going to tell us the row and another is going to tell us of the column. Okay. So let's imagine there is this program, and this is going to be, when you run this simulator, this sort of looks like it's like one step, but it's really more than that. Then we have to sort of load. So the first step will actually be collapse a number of steps in which basically our program is loaded somewhere where it's stored into the memory so that it can be run and executed. Okay, so we have done that here. We have executed, sort of loaded up the program, and done a little bit more. The IP, the instruction pointer, is pointing to 0F. That's where our code starts. So there is data before our code, and part of that is uh, the string that we want to print out, hello world. So that is stored in memory, in this case, before our program. And so we have these various sort of labels in our program. So we always had our stack pointer was sort of a built-in pointing to E7. The instruction pointer is now at the beginning of our program, 0F. And so we have other labels. So we have the start of the program is this 0F, and we're pointing to it at this point. There is a part of the program labeled print, which is at address 1.8. There is the string hello, or the beginning, and at the beginning of the string hello is at address 02. And then there is a portion of the program where we are looping, and that is labeled as address 1F. So that is our setup so far. So this is just repeating that, but with some arrows. So we have a label called start, which got mapped onto 0F. That 0F then went into got labeled as the start, and it got put into the instruction pointer. And that instruction pointer right now is pointing to that address. I'm showing that. So it's pointing to a value of 06. All right. And another thing that happened here that I want to notice is that the program you see written is sort of written somewhat in words that you can sort of understand. Move this, call that, push and pop, and things, and increment things that you sort of might recognize as instructions. And then they are put into what's in memory is not those words, but the corresponding numbers, and that's known as machine code. So we went from assembly, where we have mnemonics and words that make sense to a human, possibly, and over to numbers, which will be understandable to the computer's architecture. Okay, now I want to just show you that that the hello world is indeed in there. So we have to know a little bit about ASCII. And so ASCII is a set of 8-bit bit strings that correspond to various things. The very lowest numbers are sort of more actions than something than you do, but then starting at, say, here at a decimal number of 32, we see that is a corresponds to a space. So we have there, what do we have? We have the decimal, we have the sort of, and then we have the hex, and we have the octal. That middle one is the octal, which is not very useful to us. So we see that H corresponds to a decimal number of 72 or a hexadecimal of 48, and we're going to be seeing the 48. The little e of hello is going to be a 101. The small letters start at a 97, but by the time we get to E, it's a 101. But in hexadecimal, that's a 65. So we're going to see a 48, and then a 65, and then the L down there is 6C. So we're going to see two 6Cs for the two L's of hello. And then we're going to go, the space is going to be a 20, the exclamation at the end of world is going to be a 21. And then we're going to need to sort of know when the string is done. We need an end of string character, and we will use 00 for that. So here is just in memory, we see that before we have the instruction pointer pointing to 0F, the beginning of our program, pointing to that 06 there in the medium blue. But before that, we see our data of hello world. So the 48 for the capital H, the 65 for the little e, and so on. And that's where I'm going to end this one. And then I'm going to start the next one with actually starting to like run the program beyond just, so we've loaded the program, we're ready to run the program, but we'll end this video here.